DC. DC. And AC.
I didn't have AC.
That's okay. We're going to just talk a little bit about it. So some of y'all, this is going to be a review. Some of you is going to say, oh.
I think I learned this in motor control this morning. Wait, it's limited.
Yeah, this is the same PowerPoint. You can come up here. Well, this is stripped. This one is stripped. This is stripped down a lot.
Yeah, Mr. Foster just wanted me to teach this. I got a big gap, so I'm being this.
So since we deal with electricity and there's no prerequisites for this class, we need to have a little introduction to electricity without the math.
All right, all the math's supposed to measure.
What's it doing?
I like the PowerPoint with the formulas.
Oh wow, I need to say I'm a PowerPoint so. So introduction to electricity. By the way, I had the wrong banner up at the top. So pretest, some of y'all already know this. So this is what we're going to, and you don't. So what's a programmable logic controller? Of course, you already know that. Electrical circuit, electrical conductor, what is an electroinsulator? What metal is the best conductor of electricity? What are the two most often used electrical conductors? What is voltage, current, resistance, and power? We need to know the difference between AC and DC. We're going to be talking a little bit about this. In AC, we're going to deal with terms called cycle, frequency, and hertz. We need to know the difference between a short and an open. In fact, I don't think open's on here. I see that now. The requirements of a basic circuit. We need to know the difference between a parallel, series parallel, and series parallel circuits. And just a little bit about resistance and something called reactance. I don't think we're going to deal with reactance in this class at all because it won't even come into play. Everybody know the answer to all those questions?
Yes.
Some of y'all do. Of course, most people, when you say what's the best conductor of electricity, most people say is gold. Why? Because it's very expensive, right? Yeah. Yeah, actually, silver is the best conductor of electricity. It's not the cheapest. The actual, it is the best conductor, followed closely by copper. So we have a lot of copper conductors out there, tons of them. Followed by gold. Now, what we do, the advantage gold has over copper, and well, silver oxide is a good insulator. Copper oxide or copper rust silver oxide is a good conductor of electricity. So we have problems with the oxide flaking off and causing problems just by being out there. Copper rust is an insulator, which means an insulator, we'll look at that. That's something that impedes or stops the flow of electricity. So that means we're really concerned with copper if it gets any corrosion and stuff on it. It could add opposition in your circuit. Gold basically, as far as we know, as far as I know, does not rust. So we'll see gold used on a lot of conductors that are exposed to the atmosphere. So most of the time when they send stuff up in outer space, they'll put a gold plating on it because one thing, it doesn't oxidize and it doesn't rust, right? You understand? It's a pretty good conductor. But we gold plate stuff. So most things gold plating, you can take a nice big, pink eraser and you could erase on it just a little bit and you'll get back down to copper. And that plating is really, really thin. We do have people that works with thousands and thousands of these and they actually melt it down and restore it. But basically for us, if we wasn't really efficient, it would take more energy to melt the gold off than you would get for the gold. That's how thin it is. And you got to watch out for some of these people that sell these coins. They say gold plated with so many milligrams of pure gold. Yeah. Those most of the time you rub them a little bit with your fingers, you'll rub the gold on. Aluminum. This is a good conductor. It's not it's not as good as copper. We commonly use these for high voltage electrical conductors, and we'll look at that why. And the copper and aluminum are the most often used conductors in electricity. We usually use aluminum on these high tension, these high voltage lines. Then we get, the closer we get down to us, we'll start moving to copper. And we use a lot of gold plating. We do use silver plating, by the way, normally on switches. So if you probably took a light switch apart and tore it apart and looked at the actual two wires that come together and make contact with each other, they'll usually have a little silver plating on there. But once again, it's very, very, very thin. Be okay? So a little physics. Everybody force any interaction that attempts to change the motion of an object. In fact, to get work, you have to change the motion. So this is kind of a problem. So when we deal with physics, this is the formula for work. What's work? Force on resistance. So I come up here and I push against this wall. Am I doing any work?
Yes.
Yeah,
No, it's not moving.
Oh, no.
It's force times distance. My distance is 0. So to get work, you actually have to have distance plus a force. Power, this is what we're going to deal with. This is the rate of doing work. It's in units called watts. And the way we calculate power is we take the amount of force and then we multiply it by the speed that something's moving. And then that's work. Everybody okay? Or power, excuse me. Are we okay?
Yes.
Okay. So this is the formula that we use in electronics a lot. This is the way your power bill is calculated. So when you get your power bill every month, it's in kilowatts, right? So that would be watts. So if you got 1,000 watts and you use it 1 hour, that would be 1 hour watt. You use it over 1,000 hours, and that would be one kilowatt. I mean, right? You understand that? So basic stuff. Electrical device. All electrical devices operate off electrical current. So what's actually moving inside the circuit is something called current. The amount of work being produced by these devices is determined by the speed of the current that flows through them and the force that is causing the current to flow. So basically we're going to use force times speed. That's why we figure, that's why they figure our power bill. The speed of the current is controlled by the amount of force divided by the opposition to the flow. So every circuit's got to have opposition. So we calculate power by how much opposition something flows through. So your loads are going to have opposition to it, right? Does this make sense?
Yes.
So when we push current through a opposition, we get work in the form of watts, right? The strength and the difference of electric potential, we call it voltage, or it's also called an electromotive force. You'll run into both of these in electronics. Let's see if this guy right. I got menu. Electromotive force. Oops. We refer to this as an EMF. So a lot of books don't teach voltage. A lot of books teach electromotive force or EMF. And when they change their formulas, they'll use E instead of V in their formulas. So we'll use this term quite a bit, EMF. Or what a lot of people call voltage. I think our book teaches, our basic electricity books teach voltage, but usually when you get into the engineering programs, they'll call it an EMF. So this is our push. This is our push. It's a volt. So when you go out and buy a battery, it's rated in what? Volts. And then it's also rated in current. So it's rated in two things: how much current it can provide, and how much push does it have to provide that, push that current. Well, basically, it is a push back. What it does is it limits the flow of the current. So anytime we have an opposition, what happens is the current has to slow down, and we see that all the time, right? So I've got a hose pipe at my house, and it's got a thing that I can adjust the watt on it. I can adjust the flow. Well, what I'm doing is I'm adding an opposition in there. And as soon as I add the opposition, then the rate of the current that's moving, it slows down. And the more opposition you have, the more it slows down. The problem is that's what does the work. The oppositions are what's doing the work. So to get work, we have to have opposition, or to get power. Some materials, such as metals, allow electrons. So what we're dealing with is they found out a long time ago what's actually moving through the circuit is electrons. Yeah. So of course, so what we're doing is if we have enough push, we can cause electrons to jump orbits. And as soon as they jump one, then the electrons that pushed out becomes positive, and then another electron just pushes in. So these batteries and stuff, they're not creating current. What they do is take the electrons that's already there and cause them to do what? Move. So your metals have a lot of, they're very easy. We're not going to get into technology, but the way the electrons are set up on the metals, they're very easy to push out. All we need to do is have some type of potential on each side, and then the electrons will move. So electrons, these are jumping orbit all the time. And as soon as they jump in orbit, then the electrons become positive. I'm sorry, not the electrons. The atom becomes positive, and it looks for another electron. So all these voltage sources, all these batteries are doing, they're pushing the electrons that are already there. They're just causing them to move. It's just like a pump. A pump don't make water. What does a pump do? Pushes the water that's already there. So all we're doing is just pushing electrons. Some metals, so we already looked at that. Best conductor would be silver, but we don't run into very much silver except as a plating. Then we have copper. We have a lot of copper out there, a lot of copper. And then we have a lot of aluminum out there. But then we've got to insulate these things, and we'll talk out why. So everybody's probably saying, especially the conductors that's dropping from your transformer on wherever you're at and running into your house has got to be coated, because we don't want the two wires to come in contact with each other. That's bad. And then plus an insulator allows me to hold on to handle these wires too. So, what's that? Well, the transformers get warm. They don't get as hot as you would. Some of them get extremely hot, especially the really, really high wattage. Most transformers are very efficient, which means between 95 and 98% is efficient. But still, those low end, those 95%, there's 5% that it loses, and that's going to be in the form of heat. So your big high wattage transformers are going to be cooled. They usually have a liquid coolant in there, and they circulate it. They'll have fans and vents on the outside and radiators. I don't know if y'all seen some of these big substations or not. The ones that you have up on your pole, they're not handling that much power compared to what substations. So they'll get warm, but they won't get extremely hot. They won't get hot where you can't touch them. Huh?
I said, unless it's defective.
Or you got a short circuit, yeah. We'll look at some of we'll talk a little bit, not much about transformers. We might have some change. So we have most of our conductors are insulated. Of course, air is a pretty good conductor. So if I can get the conductors up out of the reach of humans, then we don't put insulators around them. So if you ever look at the actual power lines, they're not insulated, right? It's just only when they get down close to me and they got to run them together. So the power lines use air as an insulator. So MF is voltage. This is the difference in electrical potential that forces electrons to move. So the higher the volts, the more force you have, right? You understand? And the lower the volts. Are we okay? Yes?
Yes.
Current is the flow of electrons. That is the result of the difference in electrical potential. So anytime something moves, you got to have a difference of potential, even for wind to blow, right? You understand? So our wind usually blows from high pressure to low pressure. That's what creates wind. It's only when we mix them together right there we get big problems. Gravity is used a lot to cause water to move, right? We have pumps that create so basically pumps don't move the water. It creates a difference in potential between the input and output, which causes what? Causes the water to move. So in electricity, we're causing this thing called current to move. Resistance and reactance are opposition to the flow. Resistance does not vary with frequency. Reactance varies with frequency, and that's about the only time we'll talk about reactance. Reactance, we use devices called capacitors and inductors. They're really cool. What we can do is we can filter out undesired noise with them. We can use them to store things for a real short amount of time. In fact, the memory inside your cell phone probably uses a lot of capacitors, thousands, well, millions now, because now I think my cell phone has 16 gigabytes, which is not much. Some of y'all probably running more than that. We'll look at what the frequency is, but AC, alternating current, we call it AC, which is what Alabama Power or TVA, wherever you live at, what they generate. And then, of course, we have what we call direct current, which is called DC. So batteries create DC, and we'll talk about why we have the two a little bit in this class. So we have a unit called volts. So everybody that's looked at a battery knows this is rated in volts. So your A's, your double A's, your triple A's, these are all rated at about 1.5 volts. Right, you understand? And that's how much push you have, the push that you have. You can hook them up in series, one after the other. So if you have two AA batteries and you hook them up one inside, you'll see this done a lot in remotes. Well, if they're each 1.2 volts and you put two of them in together, that'd give you 3 volts worth of push, right? Amperes, we just call this amps, is the measure of the rate or the speed that the current is flowing. 1 ampere equals to approximately 6.25 times 10 to the 18th electrons moving past a point in a circuit in 1 second. You don't need to know that, but that's a lot of electrons. I'm still counting them. I don't know, this was all done mathematically. I'm sure nobody counted them, right? So that's a lot of electrons, but in 1 second. Electrons moving past a point in a circuit. Resistance and reactance are the measure of the amount of opposition to the flow of the current. The unit of the opposition is what we call the ohm, and we use the symbol omega. We're not going to use, of course, we're not going to do any math. We just need to have a basic understanding of this, right? Y'all have a topic quiz on all devices exhibit opposition to the flow. Conductors have almost no opposition. There is nothing out there that has no opposition. Nothing. Even supercomputers, even superconductors still have a little opposition. But instead of being up in the ohms per 1,000 feet, it's going to be down in the almost 0.00001 ohms. So currently we have nothing that has no opposition. Conductors have almost no opposition, while opposition of the load is considerably higher. Insulators have extremely high opposition. So there's nothing that has infinite opposition. So anytime I have a difference in potential, there's going to be something moving. And sometimes you can actually feel it. You know, if you get some around these high tension lines, you can actually feel it. Are we okay? Now we have a law of electricity. This is called Ohm's law. And basically it gives us the right relationship between these two. And this is not, so we can calculate the voltage. So what we do in formulas, and that's what I need to go back. So in formulas, we represent voltage times as V in formulas. Current, we use the letter I for current. And then in opposition, we use R for something we call resistance, and then we use either X of L or X of C for reactance, but don't worry about this. In fact, I need to cut that out of this class. So what we do is we have a certain amount of voltage, then we have some way we connect it to some type of load, which is gonna have a pretty good deal of R, and then we push current through that R, and then it creates work. So even your power lines get hot because they have an R component. It's just that their R component is very, very low, right? You understand that? Depends on the gauge or the size of the wire. So these are just forming. So the amount of current, so the amount of voltage we would have would be the current times the opposition, right? Understand that? And then the amount of resistance, we could take that and transpose it. We call it the formula wheel. So you just take one of these formulas, and like I said, this is something we're not going to really, and you just put what, if it's a multiplication formula, kicked off my projector.
Yeah, I learned Ohm's law by putting pi.
Yeah, that's what we do. We just call it a formula thing. We come in, and you can take any one of these three formulas, and you can do that.
You can always find out the third, right?
Yeah. So what we would do is we come up here, and if we know, that's a bad color. Oh wow, let's go to the restroom. If we know that V is equal to I times R, then we can come over here and take V and put it on the top, and then we'll come over here and we'll put I.
R.
And then what you do is you just, they say you cover up what you're solving for. So V would be equal to I times R because they're side to side. I would be equal to V over R, do this, and then R would be equal to V over I. So what happens if I've got a wire, and then just let's say it's got 1 ohm of resistance in it, and then I put 10 amps of current flow through it, then this wire, this resistor would come up here and it would drop 10 volts. And we call it, Alabama Power calls it line loss. So they're pushing current through an R, right? You understand? If you put current through an R, it's just like, when you have restrictions, and how much pressure you have is very, very important, even with you. So in you, where do they measure your pressure every time? You go to the doctor, first thing they do is measure how much pressure your heart is generating. Your heart is not moving, right? You understand? Your heart is out there, and your heart does not make blood. Who makes blood? Liver? One of them makes blood. One of the organs makes blood. Yeah, well, all the heart does is just take the blood that's already there and cause it to do what? Cause it to circulate through vessels, right? We always got, well, it depends. So we got arteries that take it out, and then we got, well, not your opposition. That's getting it out there. Your opposition would be what the final destination of the blood. So what does the blood do? The blood goes out to your muscles, right? It nourishes your muscles. So your blood would be like this resistor. I mean, not your blood. Your muscles would be like your resistors. That came up pretty fast. Let's see if we can turn our projector back on.